This is a Module 2A video on the bromination of alkenes. The mechanisms that are described here also apply to chlorination of alkenes and iodination of alkenes. And I will show the examples with 1-methylcyclohexene. The typical reaction involves a solution of the alkene in a solvent that does not react with bromine, such as dichloromethane, and dropwise addition of bromine to this solution. The reaction proceeds quite quickly and has proceeded to quantitative conversion within 30 minutes. Notice that I have used the symbol plus minus, and this simply means that a racemic mixture of both enantiomers is formed. This saves one the time of needing to draw both of the enantiomers as two separate structures. In the class meeting, I will ask you, is the reaction diastereoselective? Is the reaction enantioselective? Is the reaction stereospecific? Sometimes the chemistry in the textbook can seem rather abstract. And so last year, the teaching assistant for this course, Cameron Pratt, prepared a video showing this reaction. Cameron has given me permission to show this video. So this is in a test tube. He's adding solvent, dichloromethane, that's a magnetic stir bar in the middle. Okay, so that's the methylcyclohexene being added dropwise. It is colorless. And in a moment, he will begin adding bromine. Bromine is a dark red color liquid. Here it goes, the first drop. You can see that there's an initial orange-red color and it disappears very quickly. As he adds more, it's about the same rate, about a drop per second. Notice that the orange color persists just a little bit longer. He continues to add bromine. He's previously measured out one equivalent of bromine, and he is very slowly adding that to this test tube with 1-methylcyclohexene in dichloromethane solution. Notice what else is happening here, and we'll discuss this in class. Okay, so all the bromine has now added. Okay, so back to what the textbook shows. This is ethylene as an example of a simple alkene. The HOMO of ethylene donates a pair of electrons to the LUMO of diatomic bromine. This breaks the bromine-bromine bond and forms two bonds, one between each of the carbon atoms to the bromine. And formal positive and negative charges are formed. Positive charge on the bromonium ion, and then bromide anion as the counter anion. From Spartan, these are the molecular orbitals. For methylcyclohexene, I have shown the HOMO. Note that the HOMO has most of its electron density above and below the alkene, but there is a little bit of electron density around some of the adjacent carbon-hydrogen bonds. And then on the right is shown the LUMO of bromine. I've also provided the energy levels for the HOMO and the LUMO. And you can see that these energies are fairly well matched. The HOMO is high enough in energy, the LUMO is low enough in energy to where the electrons do not have to go into a particularly high energy orbital in order for electron donation to occur. Turning to the next page of the worksheet, I'll use curved arrow notation to show the electrons between reactants to form the bromonium ion. A pair of electrons from the alkene reacts with the empty orbital with the LUMO on bromine. There are 3 non-bonded electron pairs on each bromine atom. And one of those electron pairs, in a p orbital, donates its electrons to the carbons of methylcyclohexene at the same time that methylcyclohexene is donating its electrons to bromine. Furthermore, the electrons between the 2 bromine atoms are going onto one bromide as a leaving group, also at the same time as carbon-bromine bond formation. The bromonium ion is the reactive intermediate, which then undergoes nucleophilic addition of bromide anion to give the dibromide product. The dibromide is pale yellow in color, and that was responsible for a little bit of color that you could see in solution in the video. Before leaving this page, I'd like to show again the curved arrow notation in such a way that it is clear that all of the electron transfer is occurring in a concerted fashion. So with a fresh template, here is the electron movement. And since it is all happening in concerted form, it doesn't matter which carbon I show the arrow going between bromine and methylcyclohexene. I'll now show the Spartan depiction for the reactive orbitals giving the bromonium ion. This shows methylcyclohexene and bromine in close proximity to each other. I'll wobble the structures a little bit so that you can see them relative to each other. This is the HOMO for the entire system, but this shows a repulsive interaction between the electrons on lone pairs of bromine with the HOMO electrons of methylcyclohexene. The LUMO is more relevant. Notice how the HOMO of methylcyclohexene is lined up with the LUMO of bromine. This will be easier to see if I move this back up on the screen. So you can see the HOMO lined up with the LUMO of bromine. I've shown the bromine adding from one face of 1-methylcyclohexene, but there is equal probability that bromine will add on the opposite face of 1-methylcyclohexene. Now I will go to a Spartan depiction of the bromonium ion. This is a structure minimized for the bromonium cation. I've not shown the bromide anion, Again, I'm just rotating it so that you can see it in 3 dimensions. And here is the LUMO, which will react with bromide anion. Notice how the lobes of the LUMO orbital are lined up more along the axis of one carbon-bromine bond than the other, and have a larger volume associated with the more substituted carbon. Between the 2 carbons, bromide anion is more likely to react at the more substituted carbon to form the dibromide product. But bromide can also add to the cationic bromine of the bromonium ion to return the alkene plus bromine. So these are all in equilibrium. This concludes the Module 2A video on bromination of alkenes.